All right, so I'm going to be doing one more problem where I check the symmetry and find the zeros and the maximum R values as well as where those occur. This time for R is equal to 4 cosine 2 theta. And if you look back to your notes, this was the second polar graph that we did at the beginning of 9.7. So let's go ahead and first start by checking for the symmetry. Now, before I do, one thing that I didn't mention in my previous video, and I did that intentionally because I wanted to make sure we really focus on learning algebraically how to check for the symmetry. But if you look back to the beginning part of our notes, we did mention a couple of very quick symmetry tests right over here, which we didn't utilize in the previous problem, but we're going to use these to our advantage here specifically. And here, if you recall, I said if R is a function of sine theta, then we know right away it's symmetric with respect to pi over 2. And if R is a function of cosine theta, then we know immediately that it's symmetric with respect to the polar axis. It doesn't mean, again, that it's exclusively symmetric to just this one thing, but we do know for sure that it will be symmetric to that. So I didn't use this in my previous problem, but I am going to utilize that here. So since we see that R is a function of cosine, in this case 2 theta, but nevertheless it's a function of cosine theta, we can say right off the bat that because R is equal to a function of cosine theta, we can say therefore it's always going to be symmetric with respect to the polar axis. And that's really just due to the nature of graphing with cosine. Anytime you graph with cosine, you are going to get points that are symmetric with respect to the polar axis. You're going to have positive and negative values for R, okay, in the same exact spots for our angles theta. So since we know that this is true, we can just jump right away to just checking for pi over 2 and seeing whether or not it's symmetric with respect to the pole. Let's start with pi over 2. So if you recall, there were two ways that we could have checked for it being symmetric with respect to that angle. The first thing you could do is replace r and theta with negative r and negative theta. And let's see what we get here with that. We get negative r is equal to 4 cosine of 2 negative theta. Be careful with your parentheses there. That gives me negative r is equal to 4 cosine of negative 2 theta. And again, remember your even and odd identities. Cosine of a negative angle is equivalent to cosine of that positive angle. So we can just divide everything by negative 1 now. And r is equal to negative 4 cosine of 2 theta. So compare this with our original equation, and so far it does not look like they're the same. So at first we might say x, but really we're just not sure because we haven't done the second test yet. So let's now check the other way. The other way was to replace r and theta with r and pi minus theta. Well, let's see what this gives us. R is equal to 4 cosine of 2 times pi minus theta. Well, let's expand this over here. We're going to say r is equal to 4 cosine, and if we use our, well, before we use any identities, let's just clean that up a little bit. Multiply 2 times all of this, I should have put that up there, minus 2 theta. And if we use our identities, r is equal to 4 cosine. Now using the difference formula for cosine, we can say that this is equal to 4 times cosine, oops, let's go ahead and put some brackets here. Cosine of 2 theta times cosine of 2 pi plus sine 2 theta, or 2 pi, excuse me, sine of 2 theta. I've been doing that throughout the videos, I apologize. So, quickly evaluating this here, we know that the cosine of 2 pi, all of that's going to be equal to 1. And we know that the sine of 2 pi, all of that's going to be equal to 0. So what that really does is allow us to just rewrite this as r is equal to 4 times the cosine of whatever was left over. In this case, it's just 2 pi. Well, here we have it. We see that it's the same exact equation as our original equation. Therefore, we know that it is symmetric with respect to pi over 2. So let's write that. And so symmetric with respect to theta is equal to pi over 2. which meant that this up here actually was an equivalent equation. We just didn't know it yet. It was an equivalent equation. Again, doesn't mean it's the same equation. It just means it does result in the same polar graph. Excuse me. All right. So now the last thing for us to do is to check to see whether or not it's symmetric with respect to the pole. So I'm going to start by just plugging in negative r theta, which is the way to one way to check for the pole. And if we replace that, we see negative r is equal to 4 cosine of 2 theta. And r is equal to negative 4 cosine of 2 theta. Now, at first glance, we might just stop there and say, I guess it's not an equivalent equation right now, just because we don't have the same equation. But keep in mind what we did. We can actually leverage what we just did previously in the last part. We said that r is equal to negative 4 cosine 2 theta is an equivalent equation. And we showed the work why. And we showed just right underneath that they are indeed equivalent equations. So it turns out this is an equivalent equation. So therefore, we can say it's symmetric with respect to theta is equal to pi over 2. Excuse me, not pi over 2. What we were doing is checking for the pole here. And if that's flying over your head, just go ahead and try the second check. Just try to go ahead and, again, looking back to our notes, just go ahead and check by plugging in theta for pi plus theta. And if you want to use the sum formula again there, you'll see that you'll get the same exact equation. I'm not going to do that right now, but hopefully that's enough proof for you to see why this particular polar graph is symmetric with respect to all three: pi over 2, the polar axis, and the pole. Okay? So now next, we're going to go ahead and find the zeros. So if you recall, the zeros are, again, it's just what are the angles of theta that cause r to be equal to 0. So set r equal to 0, which means we're setting our polar equation equal to 0. And so we say cosine of 2 theta is equal to 0. And so now we're solving this double angle equation here. So we're asking ourselves, for what angles of theta would 2 theta be equal to 0? So 2 theta is equal to pi over 2, and pretty much all of the places where it's hitting the y-axis. If you recall, it's going to be, cosine is going to be equal to 0 at pi over 2, or at 3 pi over 2, or at any of those coterminal angles. So we're expressing that in this way, pi over 2 plus every pi iterations of it. So theta then is equal to pi over 4 plus pi over 2n. And again, this is just a review of solving double angle equations. So let's just express all the angles from 0 to 2 pi that fulfill this. We can say that theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And you could check your answer here. You could go ahead and plug those angles of theta back into your polar equation, and you should confirm for yourself that, yes, indeed, our r values are going to be equal to 0 every time we plug in those values for theta. All right, and last part, we're going to go ahead and check our maximum r values. We're going to see where do our maximum r values occur. Okay, our maximum r values are going to occur when, in this case, cosine of 2 theta is equal to 1 or negative 1. Again, we're asking ourselves what angles of theta would cause our r values to be the biggest possible numbers they could be. And that can only occur when cosine of 2 theta is equal to 1 or negative 1, because that's the max for cosine. So let's consider those two situations. When cosine of 2 theta is equal to 1, well, r is equal to, again, our original equation is 4 cosine of 2 theta. Well, if cosine of 2 theta is equal to 1, our maximum r value here is 4. And the absolute value of 4 is just 4, so we'll just go ahead and write that. So we have that. But we do need to consider the other scenario. What about when cosine of 2 theta is equal to negative 1? What happens there? Well, r is equal to 4 cosine of 2 theta. That was our equation. If this is equal to negative 1, then r is equal to negative 4. But because we're looking at the absolute value of r, absolute value of r also here is equal to 4. So it turns out that our maximum r value occurs in two possible scenarios. When cosine of 2 theta is equal to 1, or when it's equal to negative 1. Well, let's express that, trigonometrically. So we can say that cosine of 2 theta, if it's either equal to positive 1 or negative 1, then we're going to get our maximum r values. We just established that in the work above. So we can say 2 theta is equal to 0. Well, where does that occur? Again, think about this. Pause the video if you need to, but think about this. When would that occur? It would happen at 0 plus every pi iteration of n. Again, think about our unit circle at 1, negative 1. It's going to happen here at pi or at 0 or every pi iteration of it. So here we got 2 theta is equal to 0 plus pi n. Solve for theta. And theta is equal to 0. And let's just come up with all the angles from 0 to 2 pi that fulfill this. Pi over 2, pi, and 3 pi over 2. So if I wanted to write this kind of in its fullest form, we would say the maximum r value is equal to 4. Let's just write this when, you know what, I'll just clean that up. Why not? When, and I didn't want that guy to go along with it. When theta is equal to 0, pi over 2, pi, or 3 pi over 2. Okay? So hopefully that helps out. Now that it's our second time doing this, come up with our maximum r values, figuring out where those occur, our values for our zeros to make r equal to 0, and then really just, again, thinking algebraically about why the symmetry